Power. That's what defines a rocket. Not just size, not just speed, but the controlled fury of physics harnessed to lift steel and fire into the sky. Every time a rocket launches, it performs one of the most complex calculations ever executed by humankind. How to balance gravity, thrust, temperature, pressure, and motion, all within a few seconds of perfection. The secret lies inside the engine. A rocket's heart is a chamber of chaos. Cryogenic fuels colder than -200 degrees Celsius meet gases hotter than molten lava. In that violent reaction, chemistry becomes motion. Pressure builds, metal bends, and energy escapes through a single direction down, pushing the rocket up. Each second, thousands of kilograms of fuel vanish into a storm of expanding gases moving faster than a rifle bullet. That's thrust, the purest expression of energy ever built by human hands. SpaceX and NASA follow different philosophies but share the same obsession: efficiency through precision. SpaceX's Raptor engines are full-flow stage combustion systems, the most advanced ever designed. They run on liquid methane and liquid oxygen, circulating both in closed loops where every molecule is burned, nothing wasted. Each engine produces more than 230 tons of thrust and operates under pressures exceeding 300 bars, the same force that would crush a submarine at the bottom of the ocean. 33 Raptors together on Starship form a living organism of fire. Every engine adjusts its output thousands of times per second, creating a dynamic balance between chaos and control. The entire vehicle becomes a symphony of explosions, precisely timed, perfectly tuned. NASA's approach, on the other hand, is built on purity and endurance. Its hydrogen-fueled engines, the RS-25 seconds that power the Space Launch System, are masterpieces of clean energy. Hydrogen is the lightest element in the universe, but when combined with oxygen, it releases incredible energy. The exhaust flame is nearly invisible, the combustion almost perfect. Each RS-25 delivers 1.8 million newtons of thrust, and together they generate enough power to lift a skyscraper. They are the descendants of the Space Shuttle-era engines, so efficient that NASA decided to reuse them for the new age of lunar exploration. The nozzles, the cone-shaped ends of the rocket, are sculpted with mathematical precision. Their shape controls how gas expands as the vehicle climbs through changing air density. Too narrow, and pressure builds; too wide, and energy is lost. When designed correctly, they create a vacuum of force, a jet of plasma that carves a tunnel through the atmosphere. That thunderous roar you hear from miles away isn't random noise. It's the sound of air being ripped apart by waves moving faster than sound itself. As altitude increases, the environment changes. At sea level, the air pushes back. In space, there is nothing. So the rocket adjusts automatically, mixture ratios shift, pressures recalibrate, valves dance. It's a living equation. When fuel burns and mass decreases, acceleration rises. That's why rockets appear to speed up as they climb. They are shedding their weight, becoming freer with every second. Inside, the materials are as important as the fire. Each rocket is made of alloys so light they can flex under stress, yet so strong they can withstand the violent vibrations of launch. A rocket is not rigid, it bends, it oscillates, it breathes. Its structure is designed to survive the shaking of controlled destruction. SpaceX redefined power by repetition. Their goal was not a single perfect launch, but 1,000 consistent ones. Falcon 9 boosters now land themselves on floating drone ships, defying everything we once believed about rocket flight. That's not luck, that's data, code, and precision. Engines pivot by fractions of degrees, sensors calculate angles in milliseconds, and algorithms guide the descent through chaos. NASA, meanwhile, stands for precision in singularity. Each mission is a monument, tested, refined, flawless. Their rockets are not built to repeat, but to reach, to go farther, to carry humans beyond Earth once more. Together, these two philosophies form the backbone of modern space exploration. SpaceX seeks scalability, NASA seeks legacy. One aims to make spaceflight routine, the other aims to make history. Yet both share the same foundation: immense controlled power. Every launch represents decades of physics, engineering, and persistence condensed into one moment of ignition. The flames are not just combustion, they are mathematics made visible. A rocket's strength is not measured in thrust alone, but in purpose. Behind every countdown lies the story of human ambition refusing to stay grounded. We learn to master the violence of chemistry, to command pressure, to tame heat, and to transform destruction into lift. Rockets are the closest thing humanity has to controlled lightning. Every launch is a conversation with nature, an argument against gravity that must be won in seconds. The strength of a rocket doesn't come from brute force alone. It comes from discipline, from precision that allows violent energy to obey mathematics. Inside each engine, a storm unfolds. Cryogenic liquids rush through narrow pipes at hundreds of meters per second. Valves open and close faster than a heartbeat. The slightest delay, the smallest imbalance, and the system would devour itself. Yet, it doesn't. It stays in harmony, because thousands of engineers have choreographed the fire. At liftoff, the rocket's base becomes a miniature sun. Temperatures exceed 3,000 degrees Celsius. Pressure pushes outward like a trapped earthquake. And somehow, everything holds. Each engine acts as a separate mind. They communicate through code, constantly measuring vibration, angle, thrust, fuel flow. If one wavers, the others compensate instantly. The rocket flies not by instinct, but by orchestration. The core idea is Newton's third law for every action, an equal reaction. The greater the mass of gas expelled downward, the greater the upward force. This principle is simple in theory, but nearly impossible to execute at planetary scale. SpaceX and NASA both mastered that execution, in different ways. SpaceX turned power into an industrial process. Build fast, test fast, fail, rebuild, improve. NASA turned power into heritage, designed to endure, to represent decades of experience and national pride. One system favors iteration, the other favors perfection. Both redefine what strength means in spaceflight. The engines themselves are marvels of thermodynamics. The Raptor burns methane and oxygen in a full flow cycle, where every drop of fuel contributes to motion. The RS-25 from NASA uses hydrogen, light as air but potent as thunder. Each fuel carries its own personality. Methane, dense and reusable. Hydrogen, fragile and pure. Both demand extreme control to keep them stable. When ignited, the reaction produces an exhaust jet moving at almost 4 kilometers per second. It's invisible at first, then turns into a stream of white fire, sculpted by the nozzle into pure direction. No two stages of flight are the same. At low altitude, the air resists every meter of ascent. Engines roar at full throttle, compensating for drag and gravity's full weight. Higher up, the air thins, the noise fades, and efficiency takes over. Valves adjust the fuel ratio, expanding gases faster to match the near vacuum. From the ground, it looks like freedom. Inside the vehicle, it's a controlled descent into chaos, calculated moment by moment. The skin of the rocket is another source of quiet genius. Every plate of stainless steel or carbon composite is designed to flex under load without fracturing. It's not rigid, it sways, twists, expands, and contracts. A rocket lives, breathes, and groans under its own power. The structure behaves less like a machine and more like a living organism adapting to stress. Reusability brought a new layer of intelligence. SpaceX made rockets not just powerful, but self-aware. Boosters guide themselves home using thrusters and grid fins that adjust against supersonic winds. Computers predict motion milliseconds ahead, altering gimbal angles to keep balance. Landing legs unfold at the last possible moment, absorbing shock like muscles catching a fall. Each recovery refines the next flight's strength through memory. NASA's approach remains architectural. Its rockets are monuments, machines meant to travel farther, carry heavier payloads, and open paths beyond Earth orbit. Their power comes from scale and reliability, from mastering each component until it can operate flawlessly after years of dormancy. Both paths converge toward the same horizon, a time when launches are no longer miracles, but infrastructure. The reason these rockets are so powerful is not only the chemistry inside them, it's the intention that drives them. They are designed not for destruction, but for escape. They represent our species' refusal to stay confined to one world. Every ignition is a declaration that the sky is no longer enough. The flames beneath them are not just exhaust, they are purpose made visible. Power is not how loud a rocket roars, nor how high it climbs. Power is how precisely it obeys the impossible. Each launch is a reminder. What we once called unreachable is now a matter of timing. Each engine is a monument to curiosity. Each orbit achieved, a victory of reason over gravity. Humanity didn't build rockets to conquer the heavens. We built them to understand them,